Welcome. At the beginning of this session, I would like to review briefly the key topics we discussed in the first 5 sessions. We'll be looking at review number 1. Every current, we said, eventually returns back to its source. It seems like a simple principle, and it is, but once in a while we forget this. We think currents go to ground, but currents always return back to their source. This is true of signal currents, noise currents, and, of course, power currents. What path does current take as it's seeking a way back to its source? Well, current takes the path of least impedance. That's as specific as we can be about it until we know the frequency of this particular current. If the frequency is below 1 kilohertz, then least impedance essentially means least resistance, which basically means that currents take all the paths available, inversely proportional to their resistance. And this can be a real problem. Keeping low-frequency currents where we want them to be is not an easy situation. It's a difficult challenge. Now, for frequencies above 10 kilohertz, then currents take the path of least reactance, which generally means least inductance, which in turn boils down eventually to something geometrical that we can look at, which is the smallest loop area. So currents either take all paths available at low frequency, or they take the path of least impedance, which is least inductance, at higher frequencies. Now, of course, at higher frequencies, if currents have multiple paths, multiple inductive paths, they will again take multiple paths. They will divide inversely proportional to the inductance of the various paths. How do we know about the inductance of the path? How do we know what it is? Well, there's one very good indication. For wiring, the distributed inductance multiplied by the distributed capacitance, that product is equal to the product of the material properties, the permeability and permittivity of the material around the wires, which we don't always know what those numbers are exactly, but we do know in most cases, whatever they are, they're nearly constant, so that the LC product is fixed. If we bring wires closer together and we do something then that we know will increase the capacitance, we're pretty sure then we're going to be reducing the inductance. So that expression there will help us keep track of what inductance does. Also, excessive inductance can be indicated by excessive loop area. That's one of the key geometrical parameters that we know about that will allow us to keep track of inductance. And we know about this, hopefully, before we built the system, before we've actually assembled the wire harness or finalized the circuit board layout. Also, if wiring has low capacitance, which is what we're just talking about, if the LC product indicates low capacitance, then high inductance. And, of course, if circuits are ringing, clearly that's an indication of too much inductance. Ringing is one of our standard, most obvious clues or symptoms indicating excessive inductance. The problem with ringing is we've already got at least one prototype built, if not what we hope to be the final product. And the wave shapes are now inadequate. The wave shapes are ringing. So we have to go back and rework the system again. We'd like to detect excessive inductance earlier in the design by using loop area or capacitance ideas to indicate that the inductance is too high. For pulse-type digital signals, most of the pulse energy is below a frequency related to the transition time. Here I say rise time, but we know to use whichever edge is faster. And in a lot of digital systems, the falling edge is faster than the rising edge. So we use the sharpest edge. Now, most of the energy is below this frequency, but there is some energy at harmonics above this frequency. And for tight emission specs, we have to worry about those frequencies above this value. And for crosstalk between high-level signals, such as a digital signal, and low-level RF-type analog signals, there's energy above this frequency, which can be a problem. So if you want to know the absolute maximum frequency above which a pulse is probably not going to be a difficulty to you, you take 1 over pi divided by the rise or transition time, you multiply that by a factor of 10, and that's probably the maximum frequency we really have to be concerned about. Nothing much above that's going to give us any difficulty. Then we talked quite a bit in the first 5 sessions, well, 2 of those sessions anyway, about grounding. Why are electrical systems grounded? Systems are grounded for 2 reasons. One is safety, and one is signal referencing. We pretty much understand the safety need. We don't always, again, know the rules involved, but we know that safety grounding is necessary. In safety grounding, what we're trying to do is bond metal objects together that might become energized so as to reduce the shock hazard voltage that could otherwise exist between them. So safety grounding is bonding metal objects together to reduce a voltage difference. And the use of multiple grounding conductors is acceptable and even gives some little bit of redundance. What's the other reason for grounding? A lot of people say to provide signals with a return path. No, I don't think so. Returning currents to their sources is extremely important to us, and for signal purposes, probably more important than signal grounding. But returning currents to their sources is one thing, and grounding currents is something else. What about grounding signals to reduce noise? That's part of what we're trying to do. But I don't want to leave it stated that way, because that would give you the impression if you had a noise problem, all you have to do to fix it is simply come up with a better grounding scheme. And that doesn't necessarily work. If there are large loop areas in signal paths and you're picking up stray magnetic fields, we'll never fix that problem with a modified grounding scheme. That's an inadequate routing situation. That's a loop area problem. So what I like to say is there's safety grounding and there's signal voltage referencing. When analog and digital circuits need to have the same reference, that's an example of signal grounding or signal referencing. No significant current flows through a grounding conductor under normal operating conditions. And that is true of both safety grounds and signal grounding conductors. And again, the signal grounding conductor is not the same thing as the return conductor. It's very crucial to us in our system designs that we make a clear distinction between what are signal return conductors, which are current carrying, obviously current carrying, and what are grounding conductors. Grounding conductors carry no objectionable current. They do, in fact, carry minimal amounts, small amounts of current, even under normal operating conditions. But we try to keep that current at a minimum. There are two grounding techniques. To reduce a ground voltage difference that might be a hazard for us, either safety-wise or signal referencing-wise, we can do one of two things about this ground voltage. We can reduce the voltage to where it's an acceptably small level to not be a referencing problem or a safety problem. And we do that by trying to short out this voltage with a low resistance structure. Or we can use isolated grounding where we basically don't connect to both sides of the grounding structure. We connect to one side of the ground voltage difference. Safety laws probably require that, but we don't connect to both sides. That's single point safety grounding, isolated grounding. The ground grid or ground wire approach is best suited for very high current conditions. That's what they would use in a utility substation design. They would not in any way attempt to try the isolated or single point grounding approach. In a utility substation application, that would be a ridiculous grounding technique. It would be unsafe. It just would not work adequately at all. But for, say, low-level analog signals, particularly in the audio range, then isolated or single-point grounding would be a very ideal situation, would work very well. And isolated single-point grounding in that application would be far superior to any kind of ground grid approach. We talked about the coupling mechanisms. There are four basic ways that either signal energy or noise energy can propagate between any 2 points. Conductive coupling requires, as a basic key feature, two metal contacts. Well, I say metal, two conductive contacts. Usually they're going to be metal. But we mentioned last time battery electrolyte and seawater and things like that are conductors. They're not usually forming contacts we don't want, but occasionally they do, and they could even fall into the category of conductive contacts. Electromagnetic waves, another possible way to transfer electrical energy. To be in the far field, however, you must be at a distance greater than a wavelength. If we don't meet this condition, if we're closer than a wavelength, then we're in the near field. And if we're in the near field, the electromagnetic wave phenomenon exists in that region, but it's not the dominant problem. It's insignificant in comparison to what we got to worry about. So that's why we only concentrate on the electromagnetic wave when we're in the far field. The near field problems could be electric field coupling, which is also called capacitive coupling. Electric fields are generated by fluctuating voltages and tend to be associated more with high impedance circuits. The other possibility is magnetic flux coupling. That's through a mutual inductance. Magnetic fields are generated by pulsating currents and tend to be more associated with low impedance circuits. Let's review the equivalent circuit for each of the four coupling mechanisms that we've covered in previous sessions. Conductive coupling has probably the simplest equivalent circuit. You've got a noise source, which might be another one of our signals actually, or someone else's signal, but unfortunately that noise source is connected by a pair of wires to the susceptible system, allowing a current to flow through the susceptible system, developing voltages that should not be there. Even though this has the simplest equivalent circuit, conductive coupling is often very difficult to diagnose. We know we're looking for a pair of conductors, again usually wires carrying an unintentional current, but probably there's hundreds of wires actually involved, and we're trying to find the needle in the haystack, which two wires out of hundreds causing us the bulk of our problem. If we can prove to ourselves we've got a conductive problem, we know that filtering of some type is going to be the solution option. That's the only option for fixing conductive noise. What about electromagnetic waves? There you need a high-frequency source with an unintentional antenna usually, coupling, again, over a distance greater than a wavelength to another receiver antenna and system. Now, this other system might actually have an intended receiver, such as an FM radio or some communications receiver, or it may just have cabling that's acting unintentionally as a receiver. We can try and short out the unintentional antenna, the unintentional transmitting antenna. We can try to reduce the current on the antenna by using some common mode filtering technique. Or we can try filtering the high frequencies that are being emitted. Those are some of our solution options for electromagnetic wave coupling. Capacitive coupling, we're going to need a high frequency, well, not necessarily so high frequency, I shouldn't say. It could be 60 hertz. Electric field capacitive coupling occurs easily at those frequencies. Some kind of voltage source generating an electric flux, part of which is coupled through a mutual capacitance into a susceptible circuit. And with this circuit description, we know we can fix the problem by reducing either one of the two impedances, reducing frequency or noise voltage or mutual capacitance, disconnecting the return path, or using a shielding technique. Inductive coupling, it's pulsating currents generally, or some kind of switching currents generating a stray magnetic field. Some of this magnetic flux passes through the loop area, unintentional loop area, the one we didn't pay close attention to in our signal routing layouts. And we get some magnetic coupling. We can reduce the loop areas. That is the number one way to fix the problem. Reducing the frequency or amplitude of the current in the noise source is a great idea, but usually somebody else has control over that, and they don't like us dickering with their circuit. So controlling mutual inductance, that's the key way to fix some of these problems. Well, that's our brief review. Now we're ready to begin session 6.